Hi everyone, today we are going to present you with a short demo regarding the service provisioning pilot we are working on together with the Polish Enron PSNC for the PIONIER Network. The goals of service provisioning for PIONIER are three in total. The first was to define a standardized general workflow for service provisioning that can be used for different types of services. Then try to pilot this workflow for layer 2 circuits in PIONIER. And after this success, try to take advantage of the flexible approach and expand with other services, as well as other organizations that would like to adopt this approach. We started by analyzing the TM Forum documentation on the business process framework, started from the order to payment business process as given by TM Forum, what you see now on the slide. And then based on this, we defined our own workflow, order to payment, that goes through all of the steps defined by TMF, including the business level, such as managing client data, creating orders, tracking orders, successful or unsuccessful closing of customer orders, and billing. We are focusing not on this workflow, but on a sub-workflow inside this workflow, which is the part of service provisioning. It's inside order fulfillment. This is the part that actually configures the service on the network and makes sure that everything is running smoothly. This is the sub-process for service provisioning that we have defined in the beginning. We start with service feasibility and then go through several steps that are part of the track and manage service provisioning sub-process to finally end up with setting up service monitoring and tracking service usage. So basically inside this demo, we are going to focus on this process and specifically on the track and manage sub-process. For the implementation, we used a number of components: ordering GUI, orchestration engine, source of truth together with event listener, the Giant lightweight service orchestrator, and underneath Ansible with Jinja templates. We are doing a dry run test using a digital twin, and then if everything is okay, we work and configure the devices in the network infrastructure. Let's see first how the ordering GUI looks like. It has been implemented in React, and we decided to do it like this because Airflow is a bit specific about GUI that can be created inside it. These are all of the fields necessary to be filled out in order to be able to order a layer 2 circuit. Some of the fields, such as device and interface, what you're looking at now, are actually information that are taken from the source of truth. Others are just fields that need to be filled out here and then submitted so that one can trigger the orchestration process related to service provisioning. For the orchestration, we are using Apache Airflow. This is a free open source solution that allows you to create, schedule, and run workflows called pipelines in Apache Airflow. Mostly you define them in Python and you can trigger them any way you want. The good thing is that you can keep all of your processes definitions in a Git repo and easily change them and share them there. Apache Airflow allows you to define your own operators. It also provides integration with a lot of existing operators such as databases, SSH connections, HTTP connections, and so on. And it also offers a very nice parameterization using Jinja templates so that you can configure your workflows from the outside. It has a very functional user interface that we will show you later, and there you can see the status of all of your processes, tasks, and read logs about them, and has a powerful REST API, so you can trigger and control Airflow using an API, what we do actually from the ordering GUI. This is the UI of Apache Airflow and the list of the pipelines, or the directed acyclic graphs as they are called. We have currently 4 defined, out of which the higher level order to payment we are still not using. So right now we are focusing on service provisioning and its sub-process track and manage service provisioning. And also we use the LSO back channel as a separate workflow that talks to LSO and receives the messages back from LSO. When you choose a pipeline to take a look at the details, this is what you can see in Airflow. Basically all of the tasks that are part of the pipeline, some basic information about the DAG. There is also a graphical view of how the tasks are connected, and also you can see the code that defines the workflow in Airflow. All of the workflows are stored on Git in separate folders based on a notation that we have previously agreed to. As you can see here, the definition of a DAG is very simple and very short. That's why it's very, very easy to actually create DAGs in Airflow. This is the main workflow that is currently being called from the GUI, the service provisioning one. You can see right away here that it has been used, and you see the statistics for the usage of each of the tasks of the workflow, how many were successful, how many failed, what was the running duration, maximum, minimum, mean, and many other interesting statistics about the process and workflow itself. When you see the code, you can see how it has been created with the number of tasks that are inside, and there is also an audit log that tells you what are the last events related to the workflow, as well as some graphical information about the duration of the running, the whole workflow in different views. The other DAGs that are defined here are defined in a similar way. You can see all kinds of information about the DAGs, such as the number of successful and failed implementations of the DAG, what is the date of the last run of the DAG, and so on. So the UI of Airflow is quite easy to follow and very intuitive in this way. This is the Git repo that our Airflow instance is connected to. So it has, as you see, two folders. The DAGs that are created for the layer 2 circuits for Pioneer. These are the basic processes and sub-processes that you saw before, but now defined as Python files, while in include we have the tasks for each of the processes. And also we have information about any other integrations with different tools. In our case, this is the source of truth mod that we are using. So in this way, we are using operators to talk to the mod client, allowing others that would like to reuse the workflow and the tasks to just change these operators into something else based on the component that they are using without necessity to change anything inside the other files. Inside the configuration folder, there is a JSON that is based on a Jinja template, and these are the parameters that you can provide to the workflow without changing the workflow and thus affecting its implementation. The next component that we are going to talk about is the source of truth that comes together with an event listener. This has been implemented using Mod, which is again free open source tool developed inside the Xian project. What you see here is the GUI for Mod that has been developed specifically according to the requirements of PCNC for the PIONIER Network. As you can see, you can get a lot of information about the service. The data model is a custom data model defined by Pioneer, and it can be found at this schema location. It's based on the TMF data model with some changes and extensions and definitions. From one object, you can jump to another based on the relationships between the object. For an example, a service layer 2 circuit has two service access points. So you can see the information at the moment about the service access point and how it is related to the original circuit, but also to the interface where this service access point is currently residing. By clicking on the information about the interface, you jump to the resources definition inside MOT, and you can see that for these objects, we also store the relationship with other resources and also other services that are currently in use related to this resource. No matter if it's resources or services, you can get all of the information that is stored in the database using this GUI, which is currently read-only because MOT is intended to be mainly used using an API. As you can see here, there is also a custom schema location for defining the resources in MOT based on the requirements that were defined by PSNC, and in this case for the layer 2 circuit, basically the characteristics of model, device, and interface are the main objects that are being used together with relationships between them. Currently you're looking at the definition of an interface and the characteristic usage state and its value. It's one of the important things for the circuit. Next to the table view, there is also a JSON view where all of the information is presented in JSON, which is quite convenient if you're using the API to make changes to an object or to create a new one and so on. Regarding the interface, there are three possible usage states: active, busy, and idle. Idle is when the interface is not used by a service, active when it is used by layer 2 circuits with VLAN numbers, while busy when it is fully used by one layer 2 circuit. What you see now on the screen are the Swagger UIs for the MOT solutions. So as you see, there is a separate API for service inventory, for resource inventory, and for event listener, which is a notification hub that tells you about different events that are happening inside MOT if you subscribe to it. As I've mentioned before, the dry run is done with a digital twin. This is the digital twin of the PIONIER network implemented in Container Lab. So before the configuration is pushed to the devices, it's first checked if everything is going okay and the configuration is accepted inside the digital twin. Let's go now to the demo. Inside the demo, we are going to take a look at a number of steps that are implemented in the service provisioning workflow. Of course, the first step is to define the input parameters for the layer 2 circuit, where you will use the GUI plus the information gathered from MOT. Then we go to Airflow, which is going to examine the feasibility of the service with the information available in MOT, reserve service parameters that are used for the service, and then go to configuration, talk to LSO, try to activate the service first in Container Lab, and then if everything is okay in the network. Of course, the result from this activation is going to be stored in MOT. So we go to the ordering GUI, we choose the starting point and the end point for the layer 2 circuit, the devices and the interfaces. We provide numbers for the VLAN IDs on both ends, a name for the layer 2 circuit, such as demo layer 2 circuit, and a short description for the circuit. If we want, we can also change these characteristics and provide a community string and a value for MTU. Once we click submit, we call Airflow. And this is the message that Airflow has been called successfully. The parameters have been passed to Airflow, and now the service provisioning workflow has been started. This workflow is going to call the track and manage service provisioning, which is currently running through its tasks, and once this one is finished, then it will return back to service provisioning. The final task from there is going to be completed and the whole workflow will be completed, which is going to basically create the service and store this information inside MOT. If you're looking at the detailed information on the workflow while it is running, you can see information about the current task that is actively running and what are its outputs and how long it has taken. Once it's done, if you go to MOT and to services, you will see that we now have a new service which is called demo layer 2 circuit. Virtual circuit ID and bandwidth are types of service parameters that are being reserved inside the Airflow workflow. They were not part of the ordering GUI. You see the circuit has a relationship with 2 service access points, and it currently has a state active, which means that the activation was successful and that the circuit is implemented. We are now looking at one of the service access points. The VLAN ID number is stored here, as well as the relationship to the original layer 2 circuit and the relationship with the interface on which this service access point is residing on. If we go to the interface, we will see here that the usage state is active, meaning that on this interface there are one or more. In this case, as you see, there are more service relationships, more layer 2 circuits currently active on the same interface. This is the output that we get from the LSO, which can be seen inside the Airflow UI. And you can see in the highlighted part that LSO has returned code 0 with everything okay on both devices. This was the end of our demo. What we can see as final words and conclusion about the use of Apache Airflow inside this demo is that it's quite simple to create docs and to organize them in Git, which is a very nice feature. You can use Python, and it's quite easy to code and to implement, but you can also integrate with tasks written in other languages if you need to, using the operators feature. All of the workflows and the tasks are reusable. You just need to take the files from the Git and put it in your Airflow, and you can change them if needed. Some of the Airflow complexity is that it's very hard to develop a complex native GUI that is part of Airflow. That's why we had to develop the GUI outside in a special React application. However, the good thing is that there is an extensive documentation available with a large active community, so anything you need, anything you're stuck with, you get the answer pretty fast. That's all for this demo. Thank you so much for paying attention. If you want to contact us in the future, please use the mailing list you see on this screen, and we would be happy to collaborate with you or to answer to any questions that you might have about this demo or the use of Apache Airflow in general, or network automation and orchestration in general as well. Thank you again.